So last video we talked about how do we take a reaction that occurs in multiple steps and figure out the overall enthalpy from the individual steps. And so we did things like adding and flipping around equations. Today what we're going to do is we're going to work with an individual reaction. And in order to do that, we need to use this equation right here, this equation which says the enthalpy of a reaction is equal to the enthalpy of formation of the products minus the enthalpy of the formation of the reactants. Now, that begs the question, what is the enthalpy of formation? Well, here's what it is defined at. It's the change in enthalpy as 1 mole of that compound is formed from elements in their standard states. In other words, whenever you have a compound that is formed from its elements, either energy is going to be gained or lost when you form 1 mole of it. That is called its heat or its enthalpy of formation. It should be noted here that this little circle right here is important because that little circle means standard state. And for thermochemistry, standard state means that we're at 25 degrees Celsius, I forgot the degree right there, and 1 atmosphere of pressure. You may remember back a while ago we did STP, and if you remember STP was at 1 atmosphere, but it was at 0 degrees Celsius. Remember that? So it's kind of weird that the thermochemistry people are like, nah, we're going to do 25 degrees Celsius, but that's just the way they did it. Also, super fun fact as you go through the notes here, I've changed up my notes a little bit here to make it fit a little bit better, so you may have to arrange your notes just slightly. Now, how do we figure out the enthalpies of formation? Well, we can find them in a table. So in your textbook, they're going to have a table with all of the enthalpies of formation in them. But before we do that, let's talk about how we can figure it out or how they got it. So what you should know first is that whenever you have an element by itself, let's say you have like carbon or aluminum or even a diatomic molecule like O2, all of those have a change in H of formation of 0 kilojoules per mole. So you'll never see an element, and by the way, this is poorly written because it should read change in HF. You're never going to see an element by itself that has anything other than 0 enthalpy of formation. So when we write the formation of several compounds from elements, we call that the heat of formation. Heat of formation. Occasionally, that is also, I'm having a little bit of lag right now, heat of formation. Occasionally, that's also called enthalpy of formation, and it's symbolized by what we've already showed a couple times. We said change in H with a degree symbol and an F down below. And the F stands for, of course, formation. This seems a little bit redundant, sorry. And the degree symbol stands for standard conditions. Now, how did they figure out the enthalpies of formation? Well, let's say we were trying to figure out how we got 1 mole of NaCl. So let's put NaCl over here, and then let's just write an arrow next to it. So we're going to say, how do we get to NaCl? Well, we must have started off with Na, and that usually is a solid, and we had to put it together with Cl. Now remember, we have to put the elemental states together. So if we have sodium chloride, we're going to have sodium, we're going to have chlorine. Now, if you remember, chlorine always comes in a diatomic form. Remember Brinkelhoff. But if you take a look at this, this is imbalanced, and in order to have a change in enthalpy of formation, so change in HF, you need to have a 1 right here. That's forming 1 mole. So in order to do that, we have to put a 1/2 right here in order to get the enthalpy of formation. So it's kind of weird that we do that, but you're going to see, this is the change in enthalpy formation, and they would have calculated, there'll be some number, if you look in the table, there'll be some number in that table that tells you what is the enthalpy of formation of 1 mole of NaCl, and they got it by reacting Na with 1/2 of a mole of Cl2. Now, let's take a look at something that's even uglier. And let's say we were forming C6H12O6. Now let's take a look at the guts of this. And again, we're not doing any calculations, just want to show you how they calculated it. But if we want to get this here on this side, we have to take all the individual elements because the enthalpy of formation is always from the elements being formed. So if we start off here, we'll have carbon, won't we? And then we'll have, and if we have 6 carbon over there, we need to have 6 carbon over here. That's going to be a solid. States of matter, by the way, do matter. We're going to have hydrogen. Doesn't hydrogen always come as a diatomic molecule? It's going to look like this. So that means we need 6 of those. This is a gas. And finally, we have O2, because that's how oxygen works, and we need 3 of these. So in order to figure out the enthalpy of formation of C6H12O6, they had to figure out the energy change from these 3 things being added together. Does that kind of make sense? Now, how do we use these enthalpies of formation? Well, first of all, you need to find yourself an enthalpy of formation table, which you guys have at the back of your book, and you also have look up change in H. It's one of the appendixes, but you also have it in chapter 6 as well. But if you take a look at this, let me remind you, and I skipped over this kind of quickly at the beginning. I'm going to go back to it right now, because this formula right here is actually kind of a big deal. Because anytime you want to figure out the overall enthalpy of a reaction, you take the enthalpy, the sum of that this little E symbol right here means the sum of. You take the sum of all the enthalpy of formation of the products, and you subtract the enthalpy of formation of the reactants. So when we take a look at this equation right here, we're going to have this in the back of our head. We know that we want to have the change in enthalpy for the reaction. My computer's glitching a little bit there, but that's essentially what we have on the front page. So then we have to take a look and we have to see what are actually the enthalpies of formation. Now, I've looked these up prior. These are all in kilojoules, but because I don't want to be writing other things on here, I'm just going to write them below. So for NH3, it was minus 43. For HCl, it was minus 92. And for NH4Cl, it was minus 314. So if we go to our equation, what that means is we have to take our products, and the only thing that's on our product side isn't this the minus 314. I'm going to change color pens here because it's going to make me happier here. Let's go with this color right now. I feel like I'm like on an art show. So the enthalpy of our products, only thing we have on our product side, wouldn't it be a minus 314? And we're going to subtract all of the enthalpies of the reactants together. Now, you see we have a coefficient of 1 here and a 1 here, so it's going to be pretty straightforward. We're just going to add these two together and see how we have minus 46 kilojoules for the NH3, and we're going to add that to minus 92. Now, when we add all those together, we're going to get a change in enthalpy for the reaction of minus 176 kilojoules. And this is important. The units are kilojoules per mole, because that is the unit that we use for enthalpies of reactions. Now, when we take a look at this equation, it's a little more tricky, because when you look at this equation, first of all, it's not balanced. And let me remind you that all of our equations need to be balanced. So I'm going to jump in here and I'm going to put a 5 right here. I'm going to put a 3 right here and a 4 right here. Trust me, that is how it balances. Then I'm going to look up on the table, and remember, our enthalpy of our change in enthalpy of a reaction is always change the enthalpy of our products minus the change in enthalpy of our reactants. So in that case, let's start over here. I'm going to have a little more space here. I'm going to start over here with my products first. So do you see how I have 3 CO3s? So I'm going to look up CO3 on the enthalpy of formation table, and that's going to be 3 times negative 393.5. And I'm going to add that to 4 times negative 242. I'm deliberately keeping out the units because I'm having such a hard time with the lag. These are the coefficients. Remember, this little weird E symbol means the sum of, or adding up all of them. So we take the coefficient and we multiply it by the actual table, what the enthalpy of formation is for these. So these are all, these values right here that we're looking at, these are enthalpies of formation. So that is just our product side, right? So then we have to subtract our reactant side. And we subtract our reactant side, I obviously didn't budget very much space here. The only thing we have on the reactant side is we have this and we have this. So if we look up the C3H8, we only have one of them. So I'm going to go subtract 104. Now, the other thing we have here is we have oxygen. But remember, oxygen is an element, so its enthalpy of formation is 0. I just had a glitch there. I don't know if you can tell. Well, clearly you can tell. This is a 104. Now, when I add everything up and then I subtract, so these are my products all over here, and these are my reactants. When I subtract them all from each other, I'm going to end up with a change in enthalpy. And whenever you do for a reaction, we always like to write RXN, just to let everyone know that it's for the entire reaction. Change in enthalpy of the reaction is going to be minus 2,044.5 kilojoules per mole. Now that is a non-significant figure-friendly number, but for right now, I'm not going to pay that much attention to it. That's a lot of energy that is being kicked off, and that kind of makes sense because this is a combustion reaction. Now, those are the two basic ways you're going to see a problem presented to you. But the third way we can see it, and this is where you don't have it in your notes, you might want to jot this down, like pause the video, is they could go the opposite way. They could give you the overall enthalpy of a reaction, and notice here, they wrote COMB here. Remember, sometimes whenever you have like the change in enthalpy of a reaction, so if I write RXN right here, that's telling me that it's the enthalpy for the entire reaction. Sometimes they name the type of reaction by using abbreviation. So this is an enthalpy reaction for combustion. And they went the opposite way here, and they gave us minus 1,141 kilojoules per mole. So we know that overall, if we take C2H4 and we were to react it, and incidentally, this is what a combustion reaction looks like. So if you ever saw this and you're like, I don't know how to solve this, well, whenever you're doing a combustion, you just take your reaction and you throw it into I was going to say throw it into water. You react it with oxygen. Now, when you react it with oxygen, you are almost always going to get two things. You're going to get CO2 and you're going to get H2O. Now, as this is written, you may be like, super sweet, but this is not balanced. And much as I'd like to go through that entirely, say I have two carbons here, you have to put a 2 right here. You also need to put a 2 in front of the H2O. In order to balance this off fully, you're going to have to put a 3 right here. So this is kind of the opposite of what we did before, because if you take a look at this here, I'm going to write what we know are the enthalpies of formation, because this is the overall enthalpy of the reaction. And remember, for the enthalpy of a reaction, again, it's always the enthalpy of all the formation of the products minus the enthalpy of formation of the reactants. So I'm going to look up on the table what the enthalpies of all these formations are, because I'm looking for the enthalpy of formation of this. So this is what I'm trying to solve for right here. Now, I just happened to have looked these up before, and I know that O2, its enthalpy of formation is going to be 0 because it's an element. For CO2, and we're just talking about one individual one, is going to be minus 393.5. And for H2O, it's going to be minus 242 kilojoules. All of these are kilojoules per mole. We can think of this kind of like X, right? So if you want to set up the entire problem, we know, and we're going to set it up based on this form. I'm going to use a different color pen now again. Let's use a soothing green color. Let's dark green. So our change in enthalpy, we know that this is going to be this right here, yeah? So let's start over here, and we're just going to write minus 1,141. That is our change in enthalpy. And that's going to be equal to our products times their coefficient. So let's start over here. Do we not have 2 times what this is right here? So we're going to write for our product side, we're going to go 2 times negative 393.5 plus 2, because again, there's a 2 right here, times this. And again, let me remind you, I got these from enthalpy of formation tables, times minus 242 kilojoules. And that's all my product side. On the reactant side, the only thing I have, see there's a 0 right here? On the reactant side, all I have is my enthalpy of formation of C2H4, which is what I want to find. Now, if I just want to simplify this as a math problem, this is going to be 1,141 is going to be equal to, and this, all the stuff here, I mathed it beforehand, is going to be 1,271 minus x. And if you rearrange this, you're going to end up with your x being equal to 140 kilojoules per mole. Again, I didn't put the units in because I'm having such a hard time with the writing. I'm going to guess there'd be a decimal place right there because some of these, like 242, had 3 steam figures. I didn't see any that had less than that. But for right now, if you ever see an equation that looks like this right here, I want to go a little too far. Anytime you see something like this, this equation right here, this is your go-to, because if you have a table, which they would have to give you, of enthalpies of formation of your products, of anything, you could take your products minus reactants and figure out the enthalpy overall for a reaction. So that ends this video. The next video is going to show you how to calculate enthalpy with bond energy. Now, I will say this to you. Me just showing you this video and you not practicing on it is not going to be very helpful. So we're going to do some practice in class and a little bit for homework as well. Hopefully this has been helpful and you're able to read through all of the messiness. I'll talk to you soon. Okay, so there was one little part that I left off, and that was this table that you guys have. And I just want to walk you through how we have different, so these subscripts can kind of be helpful to us. So if you take a look at this here, the F stands for formation. That was delightfully done. Formation, it's kind of funny. This can always be got from a table. So the enthalpy of formation, and it's essentially, if you remember, the amount of energy that is either gained or lost forming 1 mole of something. Now this enthalpy of vaporization, that's when, this is vaporization. That's whenever you turn from a liquid to a gas. So if you had something like this, H2O liquid, and you went to a H2O as a gas, that's vaporization. Condensation, I don't even know if it's worth me writing these in here because my handwriting is so bad, but condensation is going the opposite way, going from a gas to a liquid. Combustion, that's what we were just talking about in the previous video. And combustion is just a type of reaction. So instead of saying RXN or reaction, which is what we do here at the very end, that just means reaction. Instead of doing that, we can actually tell you what type of reaction it is. Now, if you have a change in enthalpy and you actually have an element down below, that's a version of saying the change in enthalpy of formation. Instead of writing the actual F down here, we actually write what that is. So that is formation. It's like this, but a variation where we actually write it slightly differently. Now, change in enthalpy of fusion. By the way, you may have seen these in the previous, and incidentally, when we did this, like H2O liquid going to a gas, we saw this when we did the graphs the other day, the heating graphs, where we saw the change in enthalpy of fusion and we saw the change in enthalpy of vaporization, right? So those two enthalpies that we saw, those are actually, they're the same as this right here. Solidification, it's silly. I've never used it before, but that would be going the opposite way. This is going from a liquid to a solid. This would be going from a solid to liquid, but the values would be the same but opposite. Sublimation, right here. Sublimation, that would be going from a solid directly to a gas. And that's something like carbon monoxide or dry ice. We see that turning to a gas often. It's not a reaction, but it is a thing. A solution, enthalpy of a solution, this is actually kind of interesting because when you dissolve something, this is a solution. Again, I've kind of given up on writing here. I apologize. Well, that's much better. If you have something and you drop it into water, so let's say I have CaCl2, and I were to throw it into water and it were to break apart into Ca2 plus and 2 Cl minuses, you actually end up giving off a ton of heat. It becomes very hot. This is the principle that can sometimes happen between. I've done the same things happen with NaOH. If I take NaOH and throw it into water and try and dissolve it, it gives off a lot of heat as well. I apologize for the messiness of this, but all you have to really take away from this video is that these things down below here, all they are ways to be a little more specific on what type of enthalpy we're dealing with. Hopefully this is marginally helpful. Thanks. Bye.